15. You get to explain it here. Let's see. Best-selling book Moneyball. Michael Lewis discusses how statistics can be used to judge both a baseball player's potential and the team's ability to win games. One aspect is that a team's on-base percentage, that's the percentage of how often a baseball player gets on base, or in this case a team gets on base, is the best predictor of winning percentage. Now the reason they say that is because if you don't get on base, you can't score. So they're saying if you get on base, you have a better chance of scoring. The more you score, the more you have a chance of winning. Okay, the on-base percentage is a proportion of times a player reaches base. For example, on base of 0.3 would mean a player reaches base 3 times out of 10 on average. For the 2010 baseball season, winning percentage and on-base percentage are linear related. Let's see, so winning percentage is Y. Win percent, on base percent. Always do this, even if we're not using a graph. This just helps keep things in perspective. And I know it's a positive slope, so it's going to go like this. Is what they're saying. And they're saying that y hat equals 3.4722x minus 0.6294. And it says they're linear related and it's a positive slope. Okay. Interpret the slope. 3.4722 over 1 we write as a fraction, and it's the change of y over the change of x. I'm going to write it this way. Put it down here like this. So if this is 1, this is 3.4722. So this is percent win. This is percent on base. Okay, so on average. Because this line is just an estimate of my actual data points. My data points are just kind of scattered around it, right? So on average, for each increase of 1% in on-base percent as a team, there is associated an increase of 3.4722% winning percent for the team. Does that make sense? On average, for each increase of 1% in on-base percentage as a team, there's an associated increase of 3.4% winning percent for the team. So what they're saying is if I want to win, then it seems like I should work on my on-base percentage, at least according to this. Now, we got to be careful, because are there other lurking variables going on here? Is this a cause and effect thing? And the answer is, I don't know, because there could be lurking variables that are causing this as well. So the only thing we can really say is, according to just this data, what the slope says is, with no other factors involved, an increase of this is associated with an increase of this. It doesn't mean it causes it. So we can't say it causes this, that if I want to increase my winning, I do this. It just means there's an association between it. So we need to look and see, are there any other factors that might be causing this? Okay? Does that make sense? That's a rule. Something you got to be real careful of. So A, B. And it's easy to just go the other way. For 2010, the lowest on-base percentage was 0.298 and the highest was 0.350. Explain why it does not make sense to interpret the y-intercept. Use that information. Okay, well, I'm not sure exactly what they're saying, but let's look and see what this is. 3.4722.298. Let's see what we get if we put in the lowest uh, in minus 0.6294. Let's see what winning percentage we come up with. 3.4722.298 minus 0.6294. We get a 0.405 winning percent for the lowest one. And then for the highest, of course, we get something bigger. But I'm not sure why I want to use those. I would just plug in 0 if I had a 0 on, well, boy, this is where you got to think in context. It doesn't make sense to interpret the y-intercept just because if you have a 0 on base percentage, think about this, 3.4722 times 0. In other words, if you don't get any runners on base, are you going to win any games? The answer is no. You can't win a game with no runs scored. So you will win no games. You'll have a 0 winning percent. According to this model, you'll actually have a negative winning percent, which that's impossible because you can't win negative games or have negative percent. So it doesn't make sense. So doesn't make sense. And that's okay, because that just means our data is only good for this range of numbers. It's not valid for data when it gets down here. Our model just doesn't work, and that's okay. Would it be a good idea to predict the winning percentage of a team whose on base percentage was 0.250? Well, here's the thing. We only can use this to predict winning percentages for data that's in our range of data. So if our range of data, if it's outside the range of data, whether too low or too high, then it's not going to be accurate, because I don't know if my data is linear. What might happen is it might trail off this way, or it might trail off this way. I mean, we don't know what the data looks like. It's not necessarily going to be linear. This goes back to my classic example of heights. Heights are linear for a while, and then of course they level off. Okay? Otherwise you're going to get a 10-foot person when they're 25 years old, which doesn't make sense. Okay, so we don't know. So is it okay for a 25% on base percentage to use it? Well, I don't know what the data range goes from. They didn't tell us, so I really don't know if I could answer it. They say it's a bad idea, but I don't know here. But I would say, honestly, the best answer is going to be, it depends on the range of data given. If it's inside that range of data, then it would be okay. If it's not in the range, then it's not okay. Okay, and D, the 2010 World Series champion had an on base of 321 and a winning percentage here. What's the residual? Well, let's talk about residual. Well, the on base is 0.321 and the winning percentage is this. Okay, so they had a winning percent of 0.568. Well, what would we predict it to be? 3.4722.321 minus 0.6294. Let's see here. Okay, 3.4722 times 0.321 minus 0.6294. So we got 0.485 So check this out. Their actual winning percentage. This is actual. This is the predicted winning percentage. The residual is the difference between the two. It's the y actual minus y predicted. It's the difference. So it's 0.568 minus 0.485. 0.568 minus 0.485. 0.083, or 83%. Okay, so they performed 83% higher than what was predicted, okay, based on this model. So they did better than predicted. Okay, so that's what that means, and that's what it takes. Okay, sometimes you got to do better than what you would predict or than what you should have done. So there you go. That's it, and we'll do 16 on the next video because that was a long one.